Welcome to Engineering Innovations, the official podcast of Purdue University's Elmore Family School of Electrical and Computer Engineering. I'm your host, Kristin Malavenda, and my guest today is Utkarsh Singh, a PhD student here at Purdue ECE. His work explores nanoscale devices and new ways of detecting infrared signals using spintronic materials and what are called Poisson bolometers, and he'll correct me if I'm not saying that right later. A fascinating approach that turns heat detection into discrete, countable events instead of continuous signals. Today we'll talk about how Utkarsh ended up at Purdue, what exactly he's working on in the lab, and what life is really like as a PhD student. Utkarsh, welcome to Engineering Innovations.
Hi, Kristin. First of all, thank you so much for having me here. It's a real privilege and looking forward to this conversation.
Great. It's good to have you here. So let's start at the beginning. Where did you grow up, and what can you remember as what first sparked your interest in engineering?
Yep. So I come from the land of India, and I was born and raised in the capital city of New Delhi. And I don't really know if there was really a light bulb moment. Like, I don't know, do people have that kind of moment?
Sometimes, but okay. I think fine. Mostly, it kind of just develops naturally.
Just develops. So, as a kid, I was interested in a lot of things, but academically, I was always inclined towards mathematics.
Yeah.
So I really liked mathematics, and then in high school, physics started picking up a lot of mathematical concepts to explain reality, explain nature, and I was like, oh, that's really cool because I can see it happening around me, and I can explain things using physics, and that sort of naturally led. When I started hearing of what engineers do, and I started figuring out that we can build things using the concepts we learned in physics.
Right.
And I was like, that's even more cool because you're using nature to construct something that's useful.
Yeah.
And so that really, very gradually, very naturally sort of transitioned me towards, hey, I do want to stick to physics, but I want to do something more applied.
Right.
And that's how I got into engineering. And then it was a question of, do I want to do engineering physics or ECE? I was always inclined to both. And a lot of suggestions were that ECE is more lucrative.
Okay.
So I guess there was a pragmatic input to that as well. There's more jobs.
Yes.
And also I figured later that ECE probably has the widest scope in terms of engineering.
Right.
It touches physics. Of course, physics is at the foundation of it, but it overlaps with CS, mechanical engineering, materials engineering, a lot of those things.
Yeah, so they say wherever you have a company or something, there's an electrical engineer and or a computer engineer somewhere.
Exactly. Somewhere.
So, yeah. So how did you end up at Purdue for your PhD?
Oh, yes. So I was doing my undergrad research with my undergrad advisor, and my research was mostly on emerging nanoscale devices. We were simulating those devices to design to do neuromorphic computing, to design hardware neural networks.
Okay.
And I sort of started seeing a lot of Purdue papers popping up, like papers from groups at Purdue.
Okay.
Because be it devices papers, circuits papers, those kind of papers. And slowly on the back of the mind, it started, subconsciously, I started seeing like, hey, Purdue is getting out a lot of these papers and a lot of good ones. So when I was sitting there before my applications, I was making a list of universities. Purdue was one of the first few where I was like, oh yeah, this is a no-brainer. I have to apply to this place. So I think it's because I started seeing a lot of papers and I always wanted to get into research.
Yeah.
So that's how Purdue came up.
So when you got here, did you already know what you wanted to do research on, or has that evolved over the time that you've been here?
So I had a brief meeting with my advisor before I joined Purdue. Mm-hmm. And I also got the opportunity to present to his group. So the people I would be working with, so that was a really nice experience getting to know them. So I had a very broad idea of the project. But the thing is, research always evolves. It's like at least a 4 or 5 year journey.
Right.
And it just kept evolving because I'm sure you know this. A lot of factors are there. Funding agencies, these funding situations keep evolving.
Yeah.
PhD students as people keep evolving, their interests sort of start shifting here and there.
Yeah.
And of course, there's our PI, our advisor, and their priorities keep changing. And of course, they're the boss.
Right.
So a lot of these moving parts keep changing your research directions.
Yeah.
And especially when it comes to experiments, which is what I do, you plan something, 2 months down the line, you realize it doesn't work or it doesn't work as well. So then you have to change directions. But I've been fortunate enough that we didn't have to pivot a lot.
That's
So the
good.
broader goal has pretty much remained the same, but
Yeah.
we've changed directions quite a bit.
Yeah. That's what I mean. I think people don't realize that part of the engineering journey is failure or just roadblocks that you have to figure out a way around.
Exactly.
Your work involves nanoscale devices and infrared detection. So, for someone who's not an engineer like myself, how would you describe what you're studying?
Okay. That's a really good question. So, nanoscale devices, when I say nanoscale, it's smaller than the width of a human hair and
Okay.
probably even 100 times smaller than that.
Wow.
So, the goal is you have all these materials around you, right? For example, we deal with magnetic materials. So, if you have a magnetic material, you've seen a magnet, we've played with magnets before, but the goal is to make small structures at the scale that's like 100 times smaller than the width of a human hair,
Okay.
and then make those structures do something. And a lot of times, or in most cases, their physical properties change. So there's like this new kind of physics that happens at the nanoscale when you make those structures.
Okay.
And then those structures, then you can use to do computing, to do sensing, to do biomedical things. I think drug delivery and those kind of things. So a lot of cool and interesting things that we
Yeah.
see in sci-fi movies can be done using these like small nanoscale structures.
Gotcha.
So those are nanoscale devices, and we're using those devices to do infrared detection. So infrared is the wavelength band where the wavelength of light is longer than the visible spectrum.
Okay.
So like red light has longer wavelength than blue light. So if you go beyond increasing the wavelength of light, it goes into the infrared. And that's what we call invisible light because human eyes cannot see it.
Okay.
And it usually goes on from 800 nanometers to about 14 micrometers, or maybe even till 30. That's like a rough range.
Yep.
And the region we're focused on is called the long wave infrared, which is from 8 micrometers to 14 micrometers. And it is because all of the things at or around room temperature, including our bodies and everything,
Yep.
Emits thermal radiation in that band.
Oh, okay.
Or the radiation peaks in that band.
Yeah.
So it's really exciting because you've seen in a lot of movies, documentaries, and maybe in like and in news, in one of the surveillance and defense videos, where this show you in complete pitch darkness, you're still able to see those grayscale images,
Yeah.
people move around.
Yep.
So that is because our eyes cannot see that radiation, but we can make detectors that see those radiations.
Gotcha.
So we're trying to build a new category of those detectors, which are comprised of nanoscale devices.
Gotcha. And is nanoscale important just because of you can make things smaller, or what makes nanoscale the best way to do some of this stuff?
That's true. So smaller is one aspect, of course, but as we've seen in like computers, it turns out if you make the transistor smaller, you consume less energy.
Okay.
You can you consume less energy. You can make faster transistors, and there are added benefits. For our case, we have presented this completely new set of detectors, which, unlike previous ones, they don't require an active reset, for example.
Okay.
So you don't need to reset them. You can continuously read out.
Gotcha.
And their readout is like completely different from existing detectors. So their readout is more on the digital side.
Yep.
Existing detectors are analog. So using this completely different physics, we can have better infrared detection systems. So there are different advantages.
Yeah.
If we can try to exploit that physics in
Right.
the right way.
So one of the interesting parts about your research is the idea of, and you can correct me if I'm saying this wrong, Poisson bolometer, that detects infrared radiation as events instead of continuous signals. What makes that approach different from the traditional infrared detectors?
Yeah. So, even I didn't know how to say it. A lot of people call it Poisson.
Yeah.
I think it's a French word. They said Poisson.
Yeah.
But I think the French can say it more properly
Probably.
than us. But I'll first touch upon what a bolometer is.
Okay.
So bolometer is a category of infrared detectors where if you have thermal radiation falling on it, it gets absorbed and it heats up the material. And that heat is travels down in the detector, and then it leads to a change in resistance of the detector that you can measure as an electrical signal, like a voltage or a current change.
Okay.
So, and using that, you can quantify the light that's falling on the device, hence doing detection. So that's what any detector that behaves on this principle is called a bolometer.
Okay.
And traditionally, detectors have this, you can imagine a detector where infrared radiation falls on it, you get a deterministic signal out of it. And that makes sense.
Right.
And anything else that's noise, you try to limit that noise.
Yep.
And you have some signal and you have some deterministic readout. In this case, what we're using is we're using a noise that exists in our system. So our detector has a source of noise, and we're not trying to minimize it.
Okay.
But what we're trying to do is we're trying to observe the change in the statistics of that noise to quantify the radiation falling on the device.
Okay.
So imagine it like a random digital signal between two states. There's fluctuations between two resistant states.
Yeah.
And it's completely random. And when radiation falls on it, there's a change in that rate. The transitions increase essentially.
Right.
And that you can quantify and use to do infrared detection. So we're not trying to minimize that noise. We're playing in the field of that noise.
Right.
And the reason it's called Poisson is because it's fluctuating between two discrete states.
Okay.
So whenever you see a signal that's not analog, that's like either two states or like some discrete number of states, it's quantified by using Poisson statistics.
Okay.
So it's from a probability theory point of view.
Gotcha.
The statistics are Poisson statistics.
Yeah.
And that's why we call it a Poisson statistics or a Poisson bolometer is because we're exploiting that regime, that noise to do infrared detection. And that's how it's like completely different from traditional methods of doing detection.
So why is improving infrared detection even important? So, if your research is successful, what are we going to see in the future that results from this research?
So, infrared detection is used in, we know, surveillance, defense, it's a national security. But a lot of things that are not highlighted in documentaries we see or movies, because I also didn't know much about it before I entered the field, was that a lot of biomedical applications try to use infrared for sort of non-invasive imaging of different processes in your body. Astronomy uses the infrared band quite a bit. And now there are upcoming applications, one which came out from our group, the group that I'm at, by some other students and postdocs, which was called heat-assisted detection and ranging, HADAR. And they were able to show that infrared radiation, the infrared spectrum, has equivalent amount of information as you might see in a broad daylight visible spectrum scene.
Okay.
So, there's a lot of things you can do that are not being done because of that. And also a lot of autonomous navigation and those kind of applications are coming up in the infrared. But the thing is, infrared detectors haven't caught up with it yet.
Right.
So if you come to a lab and you'll see a bunch of infrared detectors, either they're slower or they're bulkier or they need cooling up below down to like minus 200 degrees Celsius, 77 Kelvin.
Right.
So there's an open challenge of having these low size, weight, area, and power, low swap kind of detectors.
Yep.
Because you see, visible cameras, we have some in our phones, like they're pretty lightweight. You can carry them.
Right.
They're pretty fast. But infrared detectors haven't yet caught up. And it's because there are a lot of challenges with them. And we are trying to overcome those challenges and so that we can satisfy this information-rich data capture that is needed by a lot of upcoming applications.
Right.
And you never know. Sometimes you build a better hardware and the applications follow. So there might be more. Like 10 years ago, we didn't know what applications AI might have. We had some idea, but now some new applications have come up which you have no idea about.
So you develop it and you're like, hey, wait a minute, it can do this too.
It can do this too.
So
exactly.
That's pretty exciting.
Yeah.
So your devices, as we mentioned, they're incredibly small on the order of hundreds of nanometers. What are some of the challenges that come with designing and fabricating devices? How do you even do it at that scale?
That's true. And that's the major part where, failure and a lot of frustration happens to us as PhD students and people pursuing this kind of research. So I don't personally fabricate the devices. There are other people in my group who work on them, but I am aware of the challenges and everything that they face. So at Purdue, we have this Burke Nanotechnology Center, which is really state-of-the-art facility to make these kind of devices. So you have specialized equipments where you can shine either light, visible light, or a beam of electrons even to make patterns in these structures.
Okay.
And then using that, you can sort of try to fabricate your devices layer by layer. So that process itself, since you're working at such a small scale, is prone to some variations, some defects, even the smallest impurities, if you're not careful, can damage your devices. So there's that variation part where, you're trying to build a recipe which works. and you're in an academic clean room. So a lot of groups are also using that. So there's always cross-contamination and
Yeah.
those challenges. So because of that, our yield is finite. So the number of devices we make versus the ones we have working is like, there's a difference between them. We have like a
Right.
very small fraction of them working.
Yeah.
Now, when I take those devices from them, and we're not just measuring them at a probe station, but we have built our own setup in the lab.
Okay.
So my job is to take the devices from them, integrate it with our own readout circuits that we design, and integrate that with the setup we have in the lab, and measure them and characterize them, do experiments with them.
Gotcha.
So what turns out is, electrostatic discharge. Sometimes when you're wearing woolens and stuff, there's a
Yes.
spark. Turns out even that can damage those devices
Oh.
if we're not careful enough. So we wear gloves, we wear ESD straps, but still sometimes the devices get
Yeah.
damaged. And a lot of times, and I've heard this in other groups also, is that devices sort of degrade over time.
Okay.
So if you're
Right.
measuring a device and it's like, oh, I finally found a great device and it's working out, and turns out next time you're measuring it, it's either gone or
Right.
it's like its performance has degraded.
Yeah.
So that happens all the time, and then you kind of have to start over, find a new device that's working, and
Right.
do measurements. So that part is, there are a lot of failures and a lot of frustration that happens, and we have to iterate over that, try to understand how we can make things better.
Yeah.
For example, one of the things is we realized is we have this optical table over which we put a setup. Tapping something which is not grounded also sends spikes in our devices.
Okay.
So you cannot even tap some
Oh.
for an object
Right.
that does not belong to the table or that's not grounded.
So I think that, I've talked about this before, that part of engineering is failure or roadblocks. When something like that happens and it's so frustrating, how do you kind of psych yourself up to learn from that and then move forward?
That used to be my question during my first year of PhD to my seniors, mentors
Yeah.
in my group, and they just said you have to be a little more careful and quantitative about things, where it's not just that this thing didn't work out, but more like why it didn't work
Right.
out, how much did it work out, how can we make things better. So it's more of a conscious, every week thing where you're meeting with them or meeting with your advisors and, telling them that, hey, I tried a bunch of things, this is why they didn't work out. And then it's more of a collective decision where you sit with them and decide what's the next thing is going to be.
Right.
And maybe your next decision works out in 2 months. Maybe it fails in 2 months and then you have to take another decision. So
Right.
I think that's part of the learning process, how you can make better decisions, how
Yeah.
you can plan for things better and execute them.
And viewing every situation as a learning
Yes.
opportunity as opposed
Exactly.
to just saying you failed. So what does a normal day, if there is that, what does that look like for you? Are you mostly in a lab or analyzing data or a mix of things?
I think it's usually a mix of things. So for me personally, you will find me a lot at coffee shops with my headphones on and working on things if I can.
Yep.
So you'll find me at Grey House a lot.
Yeah.
So of course I'm doing experiments. So when I'm doing experiments, I usually spend it in the whole day in the lab. I try to get some of the measurements are really long. They take 7-8 hours even.
Right.
So just measure them, and then we have to analyze that data. So whenever there's data analysis or writing a paper, making figures or working on some courses and stuff, I usually go to coffee shops and work there, or Purdue Library. We're sitting
Right.
in Walk,
Yep.
and I like coming to Walk a lot.
Yeah.
So
Just change your scenery
just
so you
change
can.
the scenery.
Yeah.
Exactly.
Yeah, that makes sense. So can you think of when you first started thinking about doing a PhD,
Mhm.
what was your perspective, what it was going to be like, and compared to what it's actually like?
Yeah, I never pursued a research problem for at least 4 or 5 years. So I had no idea that, it's going to be that long.
Yeah.
I mean, of course I knew, but when you're in it, it's a whole different feeling.
Right.
But one of the things I didn't know, what I mentioned at the start, is research direction is not just decided by you or your advisor, but a lot of other factors, like the community, what they're publishing, what are the new results,
Right.
funding agencies, what are their priorities, of course, because you're getting paid, you're getting funds to run your experiments from
Right.
because of them. So they have their own priorities. And of course, there's some wiggle room in there where you can pursue your stuff.
Right.
But I didn't know that it's going to be all my decisions that I'm going to take are going to be influenced by a lot of these things.
Right.
So that was very new for me, and I had to adjust to that because
Yeah.
that's how things work.
Absolutely.
Uh,
How does your advisor play into what you're doing, and is that a support that helps you get through your PhD process?
Of course. So I'm a bit fortunate that my advisor is not really a micromanager.
Okay.
So of course, if I'm stuck somewhere, I just tell him like, hey, Professor Jacob, I'm stuck here.
Yeah.
And then we try to figure out what can be the next best thing, or what at least we can try to get an idea on why I'm stuck or where can we go from there.
Right.
So that's pretty helpful. But he does keep taking updates from us like every week or every 2 weeks, so that he also has an idea. Sometimes, in the early years, students are stuck and they're just trying to figure things out on their own.
Right.
But that's not the best use of time. And advisors being experienced in mentoring students, they can be like, hey, stop.
Right.
This is, don't pursue that direction and, change your direction.
Yeah.
So
just give you the littlest pushes
exactly
to get you going again.
Exactly. So that's been pretty nice because it gives me room to figure things out on my own. But when I'm stuck, my advisor can see it like, hey, you're stuck. I want to do more.
Right.
But he's like, no, the risk to reward ratio is
not worth it.
Not worth
Yeah.
it. Yeah.
Was there a moment in your research when something finally worked, or when you realized you had discovered something exciting? And what was that? And what does it feel like when it finally works?
Yeah. I think that was like in my second year, where I had never done experiments before. I was doing more computational simulation designing stuff during my undergrad, and then when I worked in the industry for 2 years. Coming here, this was my first stint at real experiments.
Mm-hmm.
And I was building a readout setup where I could integrate my devices on. And I could build like arrays, not just one device, not just one sensor, but like multiple sensors on it.
Yeah.
And the whole process was a little tedious, where, I'm testing things out. I'm making sure the devices don't break, because the smallest spikes can break the device.
Right.
And then it turns out that that thing worked out on the first go. So I was really happy. But then I saw that there's going to be a bit of an issue if I continue using this readout design.
Okay.
And so I discussed with a lot of my group members, and we decided, let's do a respin. Let's design a different hardware for it. And then there was, just iterating over that. The next thing I designed, I was just fortunate enough that I thought it wouldn't work because it was a little more complicated. And but on the first go, I was fortunate. I don't know. I call it fortune.
Yeah.
There's some luck involved as well.
Right. Yeah.
But the devices just worked, and then things just worked very smoothly from there. Things worked out how we expected them to. So that was really rewarding, because a lot of times these things have a lot of things that can go wrong.
Yeah.
In fact, one of my PCBs that I designed had something printed over it that said Murphy's Law. If something can go wrong, it will go wrong. Because of how many things I had heard from my group members that had gone wrong in experiments.
Yeah.
So
it's more trying to figure it out than getting that end reward of actually figuring it out.
But things worked out in one go. I was surprised by that. So that was really nice.
That's great. Well, it gives you just enough oomph to then, keep going, as opposed to, getting distracted. For students who might be thinking about pursuing a PhD in electrical engineering, or whatever PhD, what advice do you give them?
I think you have to have a lot of interest in the area you want to pursue, because it's a long journey.
Right.
And I'm not very patient, but I think patience is a virtue that you have to develop over time to just sit with problems that are not, and things that are not working out. And I think some experience, if they can get at the undergrad level, of just how a long-term research project is, maybe 6 months or a year, just executing that will give you a much better idea of what a PhD would look like, because it's just a scaled-up version of that.
Right.
And then, of course, try to discuss with your advisors before, if you can, what I'm going to be working on, what I'm going to do. And one of the underrated things is take care of yourself, because pursue hobbies.
Yeah.
PhD, there's a lot of commitment there, but that's not the whole thing. And a lot of times students don't take care of their health and mess up their health, or just mess up their mental health, because they don't have a lot of hobbies and stuff. So have a life beyond work, whatever you're into.
Yeah. So speaking of that, what do you like to do in your free time to just relax or get your mind off engineering for a bit?
That was a great segue into this question. I think I love listening to music.
Yeah.
So sometimes I'll just sit and drink coffee and listen to music at a coffee shop when I'm not feeling very productive.
Yep.
I'll have my laptop in front of me so people would think I'm probably working, but sometimes I'm just zoned out. And music is one thing I like. I used to like sports, but because my schedule is sort of not fixed, so I just go to Corec and work out.
Gotcha.
Go to the gym and just work out.
It's a nice facility, though,
It's
too.
a really nice facility.
Yeah.
And I do love traveling. So whenever I can, I like every 2 to 3 months, I'm somewhere else.
That's fun.
Yeah. And I try to just travel as much as I can. And those are one of my hobbies. I don't have a lot. I'm not a very artistic person, but just, I guess, reading about, what's happening out there.
Right.
And a lot of those things. So that I try to do that in my free time.
Well, great. It was so great to talk to you today. Thanks so much for joining me and giving us a little glimpse into both the research you're doing and what life is like as a PhD student.
Thank you so much for having me. It was great to be here. Thank you.
And thanks to everyone listening to Engineering Innovations, the official podcast of Purdue University's Elmore Family School of Electrical and Computer Engineering. If you enjoyed this episode, be sure to subscribe and share it with someone who loves hearing about the ideas and people shaping the future of engineering. I'm Kristin Malavenda, and I'll be back next month with another new episode.